desirable feature of a control system is a faithful following of its reference input via the output. However, in most of the practical cases, this is not the case. Maybe small, but still there will be an error even though the system's output has become nearly constant. If the actual output of a control system during steady state deviates from the reference input, the system is said to possess a steady state error. This topic is actually important because in many books the formula is written little bit wrong. They have combined the cases of unity feedback system and non-unity feedback system, and the formula which we get by doing so is not right. Let's consider the first case of unity feedback system. The transfer function in this case will be equal to gs divided by 1 plus gs. C and R are the output and input of the system respectively. Generally, whenever we talk about the error of the output, it is actually equal to the ideal output value minus the actual output which we are getting. This definition is valid everywhere irrespective of which subject you are reading. But when we are dealing the control systems, then here we assume that the input signal is actually the ideal output value of our system. That's why we have written ideal output to be equal to R, which is input, but our assumption is it is actually the ideal value of the output also, minus C, which is the actual input of the system. This assumption you have to remember. This is an important assumption which many students don't know. They simply learn the equation that Laplace transform of the error signal is equal to Laplace transform of the input minus Laplace transform of the output of the system. But they don't know why we have taken the input here. It is just an assumption which is valid in both the cases, for unity feedback system as well as for non-unity feedback systems. In the block diagram also, you are going to find the same equation for the error signal which is present just after the comparator. Now, you have to simply put the value of different parameters to get the equation of error signal. ES can be written to be equal to RS minus RS dot TS. Here we have simply written CS in terms of transfer function T and input signal R. By doing so, we will get two equations of error signal which are actually the same but written in terms of different parameters. One equation for error signal is equal to Laplace transform of the input signal Rs multiplied by 1 minus transfer function of the system, and the other equation is Laplace transform of error signal is equal to Laplace transform of the input signal divided by 1 plus Laplace transform of feed-forward signal. The second equation is actually more used in numericals, but even then it will be better if you remember both these equations. Now, as we know, the steady state error is the value of error when time tends to infinity. Since we have to find the value at t tends to infinity, then it should automatically come to your mind that we have to use final value theorem here, by using which we can find the value of steady state error in frequency domain also. Steady state error will be equal to limiting value when s tends to 0 of the expression s multiplied by Laplace transform of the input variable Rs multiplied by 1 minus transfer function of the system. And the other equation is limiting value when s tends to 0 of the expression Laplace variable s multiplied by Laplace transform of input variable R divided by 1 plus Laplace transform of feed-forward function G. Now let us consider the other case, which is of non-unity feedback systems. Theoretically, our equation for the error signal has to be same in the previous case as well as in this case also. Our equation is error signal is equal to Rs minus Cs, which has to be valid here, but in the block diagram just after the comparator, the equation is quite different. Since these two equations are not the same, there is a need to do some modifications. We have simply introduced two wires, one is of magnitude minus 1 and the another one is of magnitude 1, which will obviously cancel each other out if we combine these two feedback paths. We will separate minus 1 HS and GS function and solve them and leave the other feedback path as it is. After doing so, we will be having this modified block diagram where we are having only one unity feedback path and modified feed-forward function. Now, the rest of the analysis is actually very same as we have done in the previous case. The only difference comes to the positions of feed-forward function gs. Wherever that term is present, we have replaced it with g-s. which is the modified feed-forward function. So basically, even if a control system is present which is not a unity feedback system, then your approach should be to first convert it into a unity feedback system and then only solve it. However, if you see carefully, the formula for a steady state error, which is in terms of transfer function, remains the same. But the formula, which is in terms of feed forward function, only changes. I have seen many students using the second formula, which is in terms of feed forward function, in the same way in both the cases. And that's why many students get wrong answers even though the question is very simple. You have to be very clear which formula is valid in both the cases and which formula uses modified value.